Hello everybody. Today I have another few example problems for us to go over. These are all going to involve a ship in a storm. So the first problem we have is we're trying to hoist the mainsail of the ship. I'll let you read the problem to get the context. But the important thing is that in hoisting this sail, we know that it has a mass of 250 kilograms and that each crew member that pulls on this they can pull with a steady 550 newtons on the rope. And then we're going to assume ideal pulleys and a constant speed hoist. The first problem is to draw a free body diagram for the sail as it's being hoisted. The pulley setup is arranged so that 4 rope sections share the load. So here's our sail. And it is 250 kilograms. And if 4 pulleys share the load, or 4 rope sections, that means that we have 4 pulleys. So to have 4 total pulleys, we'll say there's one here, one here, one here, and one here. So that the rope runs through this pulley, like that. And we're pulling in this direction. So on this part of the rope, we have T1, which matches over here is T1. And then here we'll call T2, which matches here is T2. And then here is T3. An important thing to realize, though, is that in ideal pulleys and rope, the tension throughout all of these will be the same. So we can just say that we have one tension T. And this is the case for, I erased the 250 somehow. There we go. Anyways, this will be the case for any ideal pulley system. The tension through any pulleys that are connected to each other will be the same. So in this case, I think we have one too many T's, and I also accidentally erased a pulley. No, we have the right amount of T's. The important thing is that we have the ideal mechanical advantage is equal to 4. And this makes sense because we have these two tensions being the same, these two tensions being the same, these two tensions being the same. Basically, we have 4 total sections of the rope. Actually, yeah, that makes a lot more sense to explain it. We have 1, 2, 3, 4 sections of the rope, all being pulled by this section of the rope. So we can say that our F net in the Y direction, we'll say we're pulling straight down, is equal to it needs to be equal to 0 so that we're pulling with a constant speed. Because we're pulling with a steady 550 newtons on the rope. In order for a steady 500 newtons on the rope to lift this sail, we need to say that our 550 newtons, I did that a little wrong. The first thing we need to do is to solve for T. So we have 4T minus the mass of the sail times G is going to equal to MA. But we know that MA is equal to 0 because we're trying to pull with a constant speed. And the 550 newtons will come in later. I forgot the reason we need the 550 newtons is because in question 2, we're trying to find out how many crew members are needed to pull the rope and raise the sail. If each crew member can pull at a steady 550 newtons on the rope. So what this is going to tell us is basically how much tension is in the rope. And with that, we'll be able to determine how many crew members we need. So we can rearrange this to solve 4T equals mg. T is equal to mg over 4, which equals 250 times 9.8 divided by 4. If you plug that into the calculator, you get that it is equal to 612.5 newtons. So this is how much tension is in the rope. And since each crew member can pull with a steady 550 newtons, we need at least two. Because one of them wouldn't be able to pull with 612 newtons, but two of them is going to be able to pull with 1,100 newtons, which is more than this 612. And that is the end of this problem. For this next problem, we have two supply crates side by side that have to be pushed off of the deck. We have crate A with mass 150 kilograms and crate B with mass 110 kilograms. 4 crew members push on crate A with a combined horizontal force of 1,800 newtons, and then we treat the deck as frictionless. First thing is to draw a free body diagram for the two crate system as a single object. So let's say we have crate A, and then crate B is a little smaller. There's a normal force and a force of gravity. And then the normal force and the force of gravity would be calculated by the mass of the total system. So instead of the just A or just B, this would be 150 plus 110 kilograms. And then there is an 1,800 Newton force. Actually, I think it makes a bit more sense in this case. Put the arrow over here. Being applied to the crates. So that's question 1. Question 2 asks us to calculate the acceleration of the two crates as they are pushed across the deck. The way we can do this is we can use F equals ma, and we know that the only force acting in the horizontal direction is that 1,800 Newton force. So this is equal to 1,800 newtons. We use the combined total mass here. We divide out the mass on both sides to leave us with A equals 1,800 divided by 150 plus 110, which is the combined mass of our whole system. And then if you put this into the calculator, this equals 6.92 meters per second squared. Question 3 says to draw separate free body diagrams for crate A and B, showing all horizontal forces, most importantly, including the action-reaction contact pair between them. The action-reaction contact pair is the same as the normal force and the force of gravity. The same way that normal force prevents the force of gravity from pulling something through the floor, the action-reaction contact pair between the boxes is going to prevent the boxes from just sliding through each other. So let's do block A first. Here's A. We have our normal force, our force of gravity, 1,800 newtons being applied in the positive x direction. And then there's also going to be, in the opposite direction, the force of B on A. And then if we have B over here, B has its normal force. It has its force of gravity. And then it has the force of A on B in this direction. And these are all vectors. The reason that the force of A on B points to the right, whereas the force of B on A points to the left, is, again, just simple contact forces. If we look at this here, you notice that B is on the right of A, which means A is on the left of B, and the forces have to counteract each other in those directions. So the last thing is to calculate the magnitude of the force that crate A exerts on crate B. So that would be this force of A on B. However, since we know that these are contact forces, the same way that normal force and the force of gravity are equal to each other with opposing directions, we can say that the magnitude of the force of B on A is equal to the magnitude of the force of A on B. We can use that now to determine the magnitude of the force that crate A exerts on crate B. The way that I'm going to do this is I'm going to take block A, and I'm going to say the net forces in the x direction on block A is equal to 1,800 newtons minus the force of B on A. And this is going to equal the mass of block A times the acceleration of block A. We already found the acceleration of the whole system earlier, and since the blocks are in contact with each other, they're accelerating at the same rate, which means we can use this acceleration we found earlier for the acceleration of block A. This means that 1,800 newtons minus the force of B on A is equal to the mass of A, which is 150 kilograms, times that 6.92 meters per second squared. We can solve this for the force of B on A, and we get that 1,800 minus 150 times 6.92 equals the force of B on A, which equals the force of A on B. If you plug everything into the calculator, you get that this is roughly equal to 702 newtons. For this last problem, we have that the ship is pitching hard in one direction, reaching a maximum tilt of 28 degrees to the horizontal. The captain, standing at the helm, has a coefficient of static friction between his boots and the wood. This is equal to 0.65. The surface is growing slicker, though, dropping at a constant rate of 0.04 per minute. We are analyzing the moment when the deck is at its maximum angle, theta equals 28 degrees. So the first thing is to draw our free body diagram. So we'll say here's the deck. So here's our 28 degrees. We'll model our captain as a box. There's a normal force perpendicular to the surface. There's a force of static friction. Sorry, let me draw that a little better. There we are. Force of static friction is parallel to the surface, opposing the direction of motion. And then the force of gravity is straight down. And the force of gravity is just going to be mg. First thing we need is to calculate the force of static friction for question 2. In order to calculate the force of static friction, we need the normal force. And the normal force can be determined by using how much of gravity points perpendicular to the surface. So we have that this angle here would be the same as this angle here. So this is our 28 degrees, meaning that this angle in the y direction is mg cosine of theta, theta being 28 degrees. This angle over here is mg sine of theta. That should all be pretty familiar at this point. So our net force in the y direction is going to be the normal force minus mg cosine of theta. But since we know that the block isn't falling through the deck, we know that it doesn't move up or down in the y direction. We also know this because if you were to model it as a horizontal here, with this being the normal force, this being the static friction, And this being the force of gravity, this force mg cosine theta, the y component of the gravitational force, normal force and the gravitational component perfectly cancel each other out. And the only thing that would contribute to this is if the gravitational force in the x direction, our mg sine of theta, was greater than the force of static friction. From all that, we can determine that n is equal to mg cosine theta. We can use this to calculate for the static friction now. If we do the net force in the x direction, we have that it is equal to 0, since this is a static problem at this moment. And this is going to be equal to mu sub s times n, which is the force of static friction. And I'm realizing right now that for this problem specifically, we have mu sub s. It's already given. So we don't actually need to calculate it. We did need to calculate the normal force, though. But we have mu sub s times n minus mg sine of theta. We'll say that this direction is our negative x direction, so that our signs make sense. Since we already calculated n is equal to mg cosine of theta, we have that this equals mu sub s mg cosine of theta minus mg sine of theta. We can rearrange this problem. We know that this is equal to 0. If you add mg sine of theta to one side and then divide by mg cosine of theta, the m and the g both cancel each other out, and then we have sine over cosine, and that is just tangent of theta. So we have that mu sub s is equal to tangent of theta, with theta being that 28 degrees. If you plug this into the calculator, we get that mu sub s equals 0.53, that is not a number, there we go, 2, and that is our static friction coefficient for question 2, which is the value which the captain will begin to slip. The mu sub s equals 0.65 is still important for how many minutes until the captain slips and the steering is lost, because we know that mu sub s drops at a constant rate of 0.04 per minute. So currently it's at 0.65. Since this is greater than our calculated value of 0.532, we know that the captain isn't slipping yet. But once mu sub s reaches 0.532, the captain will start to slip. So we can model this by saying 0.532 is equal to our initial, which is 0.65, minus 0.04 times some time. And this will be in minutes, since it's dropping at a constant rate of 0.04 per minute. This will calculate the point at which we reach 0.532. And you may realize that this looks very similar to our kinematic problem, or our kinematic equations. So if we solve for time, we get that the time, which is in minutes, is equal to 0.65 minus 0.532, all divided by 0.04. And if you plug this into the calculator, you get that this is roughly equal to, give me one moment while I plug it in, 0.65 minus 0.532 divided by 0.04, roughly equal to 2.95 minutes. So that's how long it'll take for the static friction coefficient to drop down to that 0.532. At that point, the captain will start to slip and steering is lost. That's the end of this video. There aren't any more problems for this problem set. I hope you liked it though. And as always, if you have any questions, please leave them down in the comments below.